Yeah, so here's a couple of specific cases concerning Poncelet ABC family of triangles. This one here is interscribed between a circle and a caustic, which is an ellipse, which is concentric with a circle. So I'm going to rotate this caustic and look at what happens to the projective image of ABC, shown here as A prime, B prime, C prime, as I rotate the caustic. Okay, and what I'm doing is, so the projective image as before is governed by this 3x3 matrix, and the interesting phenomenon occurs when these bottom entries are 0, so this is simply an affinity. Let's look at what happens to the locus of x3 of the projected triangle. So you can see here that the locus of x3 is rotating about its center. Perhaps this is an easy thing to prove that the loci are concentric as well. Now it's conserving the area as before. What happens to x2? x2 is actually, I think, an unstable one because, no, there it is. Yeah, this is actually an interesting result as well. x2, the locus of x2 is stationary. If I play around with the 4 entries of my affinity, okay, for example, as so, and as so. This is rather remarkable, right? Could be an easy proof. So the locus of the barycenter of the projective image of ABC over rotations of this concentric caustic is stationary. If I change the caustic slightly by moving around these base guys here, I think I can do like that. Let's make the caustic be even more, let's make it be, yeah, let's make it be more eccentric. And then let me play with these guys here a bit with the parameters of the affinity. And you can see here that the x2 caustic remains stationary. So this is example 1. If you go to x3, right, you have the same as before. You have a locus that conserves area and is concentric with the system. And then x4, let's reduce these guys here to make them smaller. Now this one's kind of interesting too. Let's see here if I can make this guy be more contained. Perhaps I can do that by, you can already see the phenomenon by making the caustic less eccentric. There you go. And then playing around with these guys a bit, my affinity. Let's make this affinity be more palatable. There you go. Maybe like that. And then when I rotate the caustic, what x4 is doing is basically just pulsating under some variable scale, but you can see here that it's basically oriented in a fixed manner, and it preserves the aspect ratio, the ratio of the semi-axis. So this is example number 1. Example number 2, which I think it was interesting as well. Let me see if I can find it. I would have to go back here to my GeoGebra examples. And how do I do this? I should be able to get back to my account by simply saying, yeah, very similar, specific manifestation. What is going on here? Let me see if everything is fine. Yes. So what I've done here is I chose a specific family of rigidly rotating caustics, namely what we call MacBeath caustics. These are caustics that have one of the foci on the center of the system. Okay, so I'm going to rotate the MacBeath caustic like so. You can see that one of the foci is staying stationary. And I'm going to look at the phenomena as before. So ABC right here is interscribed between the outer circle and this MacBeath caustic, and I'm varying, or I'm rotating the MacBeath rigidly about O, which implies that one of its foci is going to stay there. Now we know that this n equals 3 family is property rich, right? But look at what I found out when I did this. So let's animate. This is quite interesting. So in the affinity case, so now my M is an affinity, okay? You can see here that you get this extra property where the x3 locus conserves all the three, all of its 3 parameters, namely the area, the eccentricity, and the orientation. It's not stationary, as was the case with x2 in the previous example, but this is quite cool as well. Let's look at what happens to x4. x4 is also moving rigidly with a MacBeath. Look at that, how beautiful that is. Let's change the parameters of the MacBeath just slightly here. So make it be a bit fatter, like so. Okay. And you can see here that the property is maintained, that under an affinity over the family of rotating MacBeath caustics, the locus of x4 is basically translating rigidly across the plane. The locus of x3 is also translating rigidly across the plane. Now I think this is broken if I go into a full projectivity. Here we go. So now if you go into projectivity, now x3 doesn't present any interesting properties, neither does x4. Oh, x4 is basically just go back to the previous generic case of any old caustic that is rotating rigidly, namely that it only preserves area and orientation. But if you have an affinity, then you get this beautiful result. Okay, that's all for now. Thank you very much.